Okay, we are now ready to look at graphing rational functions, the last thing we're going to do as part of step 18. Rational functions just have polynomial functions for the numerator and the denominator. Kind of like these examples. Make it a little bigger. X squared over x plus 1, or 3 over x squared minus 1. And third example, 2x plus 1 over x minus 3. These are all rational functions. All of these rational functions are still going to have a vertical asymptote whenever the denominator equals 0. So just like what we practice with reciprocal functions, we just have to hone in on the denominator and figure out when it would equal 0. For instance, in our first example, x plus 1 equals 0 when x equals negative 1. That's the vertical asymptote. On the second one, if we look just at the denominator, when we solve that, and that's going to be a little more involved to solve, x squared minus 1 equals 0, we have to factor it. It's a difference of squares, which becomes x plus 1, x minus 1. This gives us x equals negative 1 and x equals positive 1. So there are actually two vertical asymptotes for this particular rational function. And then looking at the third one, it's much easier again. When does this equal 0? When x equals 3. Horizontal asymptotes are going to be a little bit more involved. We're going to need to look at the degree of the numerator and compare it to the degree of the denominator. If the numerator degree is bigger than the denominator degree, there is no horizontal asymptote. Like right here, x squared is a higher degree than just x. So we would say there is no horizontal asymptote. Case number 2, what if the numerator degree is less than the denominator degree? If that happens, the horizontal asymptote is just the line y equals 0. Like right here. The degree of the numerator is just a constant, so that's a degree 0. And there, the degree of the denominator is 2. So our horizontal asymptote is just y equals 0, or f of x equals 0. Third case, what if the degrees are equal? No matter what the degrees are, as long as they're equal, we're just going to look at the leading coefficient of the numerator and the leading coefficient of the denominator. And we're going to make them a ratio, and that is our horizontal asymptote. Like right on this example here, example 3. Notice they both have a degree 1. So I'm going to look at the leading coefficient of the numerator and the leading coefficient of the denominator. It's invisible, but there's a 1 right there. So my horizontal asymptote is going to be y equals 2 over 1, which is just 2. Let's practice graphing some of these. Our first one is x cubed over x minus 1. Find the zeros. Well, one option to find the zeros is to use our table, which we're going to do in step 3. But another way is to set the numerator equal to 0 and solve. So if we say x cubed equals 0, we would need to take the cube root of both sides, and we end up with x equals 0. That is one of our roots or solutions, our zeros. And that means the graph is going to cross the x-axis at x equals 0. That's what it means. Now let's think about vertical asymptotes. Just like before, we're taking that denominator, setting it equal to 0. This is where it's undefined. Solving. When x equals 1, there is a vertical asymptote. we're ready to graph this. Oh, actually, let's think about the horizontal asymptote. The degree of the numerator is bigger than the degree of the denominator. So what does that mean? Degree of the numerator is bigger than the degree of the denominator. No horizontal asymptote. So let's add that so we don't forget. No horizontal asymptote. Let's go ahead and graph x equals 1. It's a vertical line right here. So we know our graph will not cross. We do know that the graph crosses the x-axis when x equals 0, so there is a point right here. Go ahead and include that on my table. Now to find the rest of these values, let's just use our table in Desmos. Here you can see I've typed the function into Desmos. I'm going to press the gear shift and the table, and immediately I see some values. But I want to complete the table that's in my notes, so I also want -3. So I'm going to hit enter and say -3. That would be the point, positive 6.75. -2 gives me 2 2/3. -1 is 0.5. 0, 0. 1 is undefined. It's not even listed on our table. Our table does ask for 1/2, so let's try 0.5. I'm just typing that in and I get -1/4. 1.5 gives me 6.75. 2 gives me 8. Let's see what 3 gives me. 13.5. That's probably going to fall off my graph. Alright, let's go back and plot these points now as best we can. -3 up 6 3/4. -2 up 2 2/3. -1 up 1/2. 1/2 down 1/4. 1 1/2 up 6 3/4. 2 8. Let's make sure we count correctly. 2 4 6 8. And like we said, 3 13.5 would fall off the graph. Now, again, we need to look at the picture of our graph so we can kind of see what we want to make it look like. It comes down, and then it curves around the 0 and continues on, approaching x equals -1 or x equals 1, but it doesn't cross it. And then it picks up at the top and connects those dots. So we're coming in here, and we're approaching that asymptote, but we never cross it. Similarly, we come down from the asymptote and go back up. There's our graph. Let's talk a little bit about oblique asymptotes. These are sometimes called slant asymptotes. Sometimes when we don't have a horizontal asymptote, it's because it's an oblique asymptote. If the degree of the numerator is just 1 degree bigger than the degree of the denominator, we will have an oblique asymptote where we need to take the numerator divided by the denominator, and that will be the equation. So if you think back to when you used to divide polynomials, which has been probably a little while, we're going to take x to the 4th plus 3x cubed. We're going to divide it by x cubed minus 1. So I'm thinking, what times x cubed gives me x to the 4th? And the answer is x. X times x cubed is x to the 4th minus x change the signs because we subtract here. These cancel, and I'm left with 3x cubed plus x. They can't go together because they're not like terms. Now I'm thinking, what times x cubed gives me 3x cubed? And the answer is 3. 3 times x cubed is 3x cubed. 3 times negative 1 is negative 3. Change the signs of everything that we've just written. These cancel, and I'm left with x plus 3. Now, the equation of the asymptote is our quotient with no remainder. So our asymptote equation is just x plus 3. So if I were to graph that, I would go and begin at 3 and go up 1 over 1, up 1 over 1. That's where we're getting this slanted dashed line that helps determine the shape of our graph. Let's try one together. Notice the degree of the numerator is 2, and the degree of the denominator is 1. They're 1 apart, which means we can divide. So we're going to divide 2x minus 1 into the numerator. X squared plus 4x plus 4. Go ahead and pause the video and try that division problem. So it's certainly not the prettiest division problem, but if you use your calculator and work well with the fractions, you will end up with this asymptote. So we're going to put that under step 2. That's our slant asymptote. It's the line y equals 1/2 x plus 9/4. Let's do the vertical asymptote next, since we're already looking at that. We're going to look right at the denominator. When does the denominator equal 0? Adding 1 to both sides, we have 2x equals 1, divide by 2, when x equals 1/2. So that's our vertical asymptote. Now we need to think about the zeros. When will the numerator equal 0? Well, if we factor this to solve, we get x plus 2, and then setting each piece equal to 0, x equals negative 2 for both of them. So that ends up being our 0. X equals negative 2. So when x equals negative 2, we're going to cross. Let's go ahead and draw in our asymptotes. We have a slant asymptote which starts at 2 1/4. I know fractions aren't the nicest, so we go up 1 over 2. 1 over 2. And this is our slant asymptote, or our oblique asymptote. We can connect them with a dotted line. We also have a vertical asymptote when x equals 1/2, which would be right here. And now we can go ahead and pull up Desmos to type in our function to find out a few other nice points. So in Desmos, I'm going to clear out what's there. You can put the f of x, but you don't really need to. We do have a fraction, so I'm going to start with a division sign. X squared plus 4x plus 4 in the denominator, 2x minus 1. So this is what our picture should look like. If we look at our table of values, we get some fairly nice points here that we can graph. It's kind of hiding. There it is. Okay. Going back to the graph, we already have the point 0 or negative 2, 0. It's already on there. Grab my blue pen. Okay, we want the point negative 1, negative 1/3. Should be here. 0, negative 4 is on our graph. 1, 9 is on our graph. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. The point 2, 5 and 1/3 is also on our graph. Should be about here. It's just a little bit past 5. We can try for a few more points. 3, 5. 4, 5, and a little bit past 5. And we're just trying to get an idea of what this graph will look like. So notice, because we have the asymptotes, we know how to fit these without crossing it. Same with our other branch. We're approaching the asymptote, but we never cross it. It just progressively gets closer the further down it goes. And there's our graph. The last thing I want to talk about is point discontinuity. Sometimes you have a function, and when you factor it, factors cancel out. Remember when we were simplifying our rational functions earlier in this step? And we're left with just a linear equation. And if you graph that line, it would look like this line, but there's going to be a hole in the line. That's called a point of discontinuity. For example, with this one, if I factor the numerator, the difference of perfect squares, and put it over my denominator, notice the factor of x minus 4 cancels, and I'm left with x plus 4. So to graph this function, all I have to do is graph the line x plus 4, begin at 4, up. Graph that linear function. Takes us all the way back to algebra 1. Connect this line. But there's going to be a point of discontinuity, just like in our example here. We're going to zero in on our original denominator, x minus 4. It would be undefined when x equals 4. And that means that we're going to have a hole when x equals 4. 1, 2, 3, 4. There's a hole. And you need to make sure you draw a hole in your graph, or it would not be correct.